So we are going to present here the general strategy that we're going to follow for the numerical resolution of the first order ordinary differential equations that we are going to consider. Okay, first let's present again which the ordinary differential equations that we do have. This is that's the equation. Uh, we're going to call the function is going to be y, and the independent variable it's t. So the derivative we do have here that derivative of the function y with respect to t is some function that depends on t and y. Besides that, as this is the first order differential equation, we do need one initial condition. In this case, this is the initial condition that we do have. So that basically means that in this graph here, we do know what's going to be the starting point for this y function. It's going to be this one, according to the initial condition that we do have here. And the evolution and how it evolves, how it moves, or how it's going to be from this time on will depend on the uh, differential equation that we do have here. So the first important thing is that when considering the numerical resolution, we cannot solve at any point at any time t. We have to predefine previously which are the times that we are going to apply the numerical method. So basically we are going to have to define some mesh on the time variable. And that's going to be the mesh we are going to consider. So basically it means that if you consider, for example, here that this is the last time, we're going to call it capital T, where you want to calculate your y function, you have that the time range where you have to calculate your y function basically is t capital T minus t0. And first you have to predefine how many time intervals that you are going to define in this time interval, which these time intervals are going to predefine the mesh that you are going to consider for the time variable. So let's consider we're going to define n intervals. Therefore, the time interval we're going to define, which is going to be delta t here. So I mean the time difference from one point to the other is going to be the ratio between this one over n. So that's important. So that's the beginning. We have to predefine the mesh in the time variable. And once we have predefined this mesh, the aim will be to apply different numerical methods in order to get the solution for this equation here. And in order to get the value of the y function for each time step we have defined in the mesh. So let's consider that applying that method, we are getting that the y function evaluated at time t1 is, let's say, for example, this value. Or we're going to call it y1. The y function evaluated at time t2, let's suppose, is this value, y2. And therefore, just considering that, we can interpolate these values here in order to have the curve, corresponding to the time evolution of the y function. Of course, it's going to be the higher the number of points you're going to define the time mesh here, the more accurate it's going to be the wave function, because it's going to be evaluated in more time steps. However, we have to take into account also how long it takes to make the calculation, because let's suppose it's very long, so you cannot make very high number of, we cannot consider in this case, a very high number of time steps. So at the end, it's everything. It's like a balance between accuracy and the time you require to make the calculation. So this is more or less the general strategy that we are going to follow in order to apply different numerical methods. So the first part is going to define the mass, and then we have to define different numerical methods we are going to apply in order to using the information on the y function evaluated at different time intervals in order to have, for example, the y function for the next time. And that's what we're going to do next.